Welcome to my channel. Um, Today's topic is a very complicated topic, and if you do not like long videos, click off now because this one's a long one. And this one has to do with space travel. So if you're not interested in space travel or long videos, click off now. Uh, for all the rest of you that might be interested, if you like this sort of discussion, leave a like below. If you like leaving comments and you have some ideas, something that's positive, and you can put some effort into putting forth a statement that might be helpful, comment below. If you have anything negative to say, keep it to yourself. I don't need you trolls out there trolling me right now. So here's my disclaimers. 1, I'm not a scientist. 2, I didn't complete high school. And 3, I have a bias against any use of monetary funds or materials that do not benefit the planet, which is our core life support system currently. If we can't benefit the core life support system we have, then going to space is not going to help us. First, we have to make our planet livable for the inhabitants of the planet, and then we can think about going to space. We have to not be in a war. We have to not have homelessness. We have to solve food problems here on the planet before we go shipping massive amounts of energy, money, fuel, and resources to a spaceship that may not be inhabitable. So we're going to go over that right now. Space travel. I don't care if you go to the moon. I don't care if you go to Mars or Pluto with your space rocket. It doesn't matter if you're just orbiting the planet. This still applies. This information still applies. 1, regardless of the fact that you had to build the space station to start with and get all the materials, raw materials, up into a stable, not degrading orbit. In other words, not an orbit that's in decay and is going to have the space station fall back to Earth and hit the planet again. It has to be stable or greater than stable. And I don't know how you get there, since you got to get past physics first. The space station cannot return to Earth without a way to disassemble itself without crashing into the planet. And there's serious reasons behind that, like global devastation. So we have this beautiful rock that spins around our planet called the moon. And if you've ever looked at the moon, it's cratered. And we're not talking some small craters. We're talking gigantic, huge craters. Craters large enough that we think that looks like a face. So if my head is the size of the moon, God, that would be awesome. If my head is the size of the moon and my eyes are 2 craters and my nose is another crater and my mouth is another crater and you have a face looking at you from the moon, how big are those craters on the moon? So we have a shield. Don't forget it. Here on Earth, we have perfect examples of meteorite impacts. And I guess they call them meteorites because asteroids are in space and meteorites are in atmosphere. Whatever. You have a rock or a comet or some debris that fell to the Earth, smashed into the planet's surface, knocked a huge amount of debris into the atmosphere, and caused global devastation. You don't want to do that with your starship. So the larger the ship gets, you got to think about it. It becomes a kinetic energy weapon. And if it falls back to Earth, it can reach speeds over 40,000 miles an hour. Well, mass times velocity equals force, I believe, right? And when it hits, that force is going to get released in the form of energy. Kinetic energy is going to strike something else, and stuff's going to happen. So the orbit of the object has to be stable or greater than stable. In other words, it has to be able to leave the atmosphere leave low Earth orbit, get past an orbit that it will decay and fall back to Earth. So just saying, any of those space stations that you don't want falling back to the Earth and crashing into the Earth and causing a global devastating problem, you're going to have to figure it out. Okay. You've built the space station. You've got into a non-decaying orbit somehow. And you have to deal with ionizing radiation. Now, the last time I checked, basic science classes from grade school to high school, and I didn't go to college. I don't have a college degree. Matter of fact, I don't really have a degree in anything. Baseline physics from third grade all the way up to high school, as far as I know, tells us that we have an electromagnetic spinning core made of nickel iron. Now, that's great. Everybody goes, ooh, so what? Electromagnetic core. We're creating an electromagnetic shield around the planet. Ooh. So the core is spinning, and it's putting out electromagnetic waves, right? And it just so happens that those electromagnetic waves are intersecting cosmic rays and bouncing them off, keeping us from being ionized by solar radiation as well as cosmic radiation. Now, I could be wrong. It's possible. I'm not a scientist. But if I'm right, your starship or your space station has to be able to shield itself from ionizing radiation, or the inhabitants will get cancer and prematurely die, and it just won't be a good thing. So you got to get past ionizing radiation, and that means you have to have some form of deflector shield or electromagnetic shield. And the way we know that to be true is if you go up to Alaska, you can see the aurora borealis effect. And the last time I heard, that was highly charged particles entering the atmosphere and interacting with the electromagnetosphere, bouncing those ionizing radiation rays off and causing the lights of the aurora borealis, as well as some interaction with the atmosphere. I could be wrong. I'm not a scientist. But if I'm right, and scientists are right, then you have to have that on your starship or your lunar module or your Mars module where you're going to survive, because the moon doesn't have an electromagnetic spinning core. And as far as I know, and I could be wrong, Mars, being smaller than the Earth, also does not have an electromagnetic spinning core. I don't know. I never took those measurements. Could be wrong. But also, Mars doesn't have an atmosphere of any appreciable nature. So that's not helping, because our atmosphere is 7 miles to 8 miles of useful atmosphere, because we can fly planes at 34,000 feet. That's still useful atmosphere. And then after that, it gets kind of thin. It keeps getting thinner and thinner and thinner as you go away from the planet, until it's not noticeable, and we call that low Earth orbit. And that could be 250 miles from the surface. Whatever. There's not a lot up there, is the point. So you no longer have the rough 7 or 8 miles of useful atmosphere, of dense useful atmosphere that's helping deflect solar radiation and the remaining cosmic rays that are coming in and diffuse that energy over the total surface of the globe. And you can see that effect every time you see a cloud. Water vapor is great at diffusing light. It's a fairly dense material compared to atmosphere, and water vapor can cover 60 to 70% of our planet's atmosphere at any one time because there's so much water volume in atmosphere. But I could be wrong. But we like to call that cloud cover. And that cloud cover is diffusing the radiation and absorbing it and changing its direction a little bit, reflecting some of it back to space. So there's reflection, absorption, diffusion, and I'm forgetting the others. Whatever. Whatever remains is the visible spectrum, the infrared spectrum, and anything like X-rays and gamma rays that are coming through that, we couldn't stop anyways. It doesn't matter. Because the sun puts out a huge amount of spectrums of light. Whatever. So your Starship, your International Space Station, gets into a non-decaying orbit. You've created an electromagnetic shield to reduce the ionizing radiation. You built the thing. Hey, it cost some money. You did it. And then you have a supply chain problem. You're no longer attached to the Earth. So anything that's above the Earth has to get supplied because it doesn't supply itself. And Earth down here is the supply of everything we know in the history of man. Now, there's a theory that you could go from here and you could go to an asteroid and grab the asteroid and bring it back to here and make things work. Okay. That could take, to get to an asteroid that's of a significant size and actually grab it and have the technology to grab it and then turn around and change its motion of its mass out of orbit to come to you and add mass to your thing. So you're bringing the mass down to this. Well, you're changing things that you may not want to change in a non-decaying orbit by adding mass. Okay, so you bring some mass in. What happens to your orbit? Does it start to decay? Do you have enough fuel or propellant to raise your orbit to stop a decay cycle from causing you to come back down? That's even if you could grab how many metric tons of mass that's moving at very high velocities and turn it enough to come back to you, let alone push it to come back to you. The likelihood of that actually happening is significantly low. It's very low. Versus here's Earth and here's your ship or your shuttle or your space station, and you send something up to the space station and then the Earth is still here and this thing got some more material. And you send it up. It's much shorter distance, dynamically shorter. It's calculable. You could put a $sign on it. You may not be able to put a $sign going on finding an asteroid and turning it around and bringing it back. So your supply chain is an issue. If you don't have a supply chain that's stable and economical and viable, you can stop there. Somehow you got past building the thing. Somehow you got past the ionizing radiation to stay on the thing. And then if you don't have a supply chain that's stable, you're done anyways. So no supply chain, no worky. Here on Earth, if we don't have water, most construction stops. If we don't have water, most humans stop. And if we don't have water, most waste cleanup stops. That's from everything from cleaning windows to cleaning dust off solar panels to cleaning terminal ends on all kinds of machinery. It doesn't matter. You need water. No water, no supply chain, no work. Okay. So somehow you got this thing, built this thing, fixed ionizing radiation, and you secured a supply chain. You welded the thing together or bolted it together or whatever fabrication method you used. All mass, even in space, is going to expand and contract due to thermal expansion and contraction. This is going to cause hull stress. Under normal welding conditions here on Earth, and welding is a medium that I utilize to build and fabricate things and make money. So I have to understand welding fairly well. I used to sell the equipment. We had a welding supply station for a long time. I became a welder fabricator. I'm a blacksmith, so I understand metals fairly well and construction methods fairly well, and I work in construction for my income. And thermal expansion and contraction is fairly simple. It's when things get hot, they get agitated and they typically grow a little bit. Not too much, but they do expand a little bit. There's very few materials that don't. Almost all materials heat up and expand at some level. Thermal contraction is when things get cold and the molecules stop agitating so much and they slow down and they get closer together. Now, I'm not a physicist, so I could be totally wrong on this, but I am a welder, and we can't have warpage in our welds. We have to have flat, straight welds when we work, and we have this thing called a heat-affected zone. So when we do some welding, that zone of welding is got multiple problems. It's fantastic medium to work with, really strong, usually changes the characteristics of the base metals to be stronger, but that can cause embrittlement if you do it wrong or use the wrong materials or have the wrong speed or the wrong heat or XYZ. And wrong shielding gas and all this stuff. We go over all those finite details, but the heat affected zone, small though it may be with welding techniques in space, because they may be able to use TIG welding, or they may be able to use electron beam welding or laser welding, or even MIG welding without the gas, because there's no need for gas here because there's no oxygen or nitrogen to get in the weld bead. Doesn't matter. Regardless of the heat affected zone is going to be slightly different chemically and elementally than the base metals. And the base metals have to have very high purity, by the way. And then when two objects are welded together, so object A and object B, and you put them together and weld them together, there's a seam, and that seam has a third metal that usually was welded into it, unless you have autogeneous welding, in which case you bond the two metals together, and there's going to be a gap and high and low spots. But if they are slightly out of alignment, ever so slightly, there's going to be a weak point there where they can break away. And every time the expansion joint happens, expands and contracts, that's going to cause metal fatigue. And then it's going to, sooner or later, it's going to fail. Okay? And that's just from the stress of heating and cooling over time. We haven't even gotten into anything else yet. So on the sphere that's spheroid, or the tube that is being designed to be utilized as a starship or a space station, this is going to be the sun side, and this is going to be the dark side. And the sun side could be 200 plus degrees, and the dark side could be -60 or -80 degrees. So this one's expanding and this one's contracting. And then if it rotates, then this contracts and this expands. And as that happens over and over and over again, you're going to get warpage and expansion joint cracks, and it could be all bad, especially if the thing is spinning and it's changing its temperature constantly. It's not consistently the same temperature at all times. So that also includes the fact that the internal volume, the volume inside the tube, is also expanding and contracting. So it could be expanding and then contracting, and it could be doing this on the inside with pressure. Now, because humans live in 14.14 psi at sea level, wow, 14 psi, that doesn't sound like a lot. That's the total atmosphere above us crushing down on us. 14.14 psi, roughly. Depending on who took the measurement. It could be 14.147. It could be 14.15 at sea level. I'm not a scientist. I didn't take that measurement. We consider that to be baseline, which is 14 psi. So we have to create 14 psi inside the total volume of this tube. Okay? So you're forcing expansion on the whole system by 14 psi, and there's a vacuum on the outside. So the thing wants to come apart. Anybody see a problem with that? The larger the surface area, the total PSI, pressure per square inch, last time I checked, pushes on all the surfaces equally to create 14.14 PSI internally with 0 PSI on the outside. So there's this beautiful system of pressure differentials, and where energy is high and energy is low, the energy high will want to go where the energy is low. Well, where's the energy high? Inside the spheroid or the tube or the Dyson sphere or the tube or the torus or whatever you want to use. I don't care the system. I don't care the shape. I don't care the geometry. It doesn't matter. 14.14 psi wants to get out to 0 psi and equalize. So if there's any cracks, however minute, in any of those welds or fabrication techniques, the pressurized gas will find that hole and it will leave. Now, how do we know this to be true? It's a good question. NASA found out the hard way. Now, NASA here in America has been sending shuttles up on a regular basis to low Earth orbit, and they found out a particularly interesting problem. As well-funded as NASA is, and as wonderful as their technology is, they had a short duration of time and space. And the reason for the short duration of time and space is due to leakage. It's not because of fuel. It's not because humans got tired of being in space. It's not because they ran out of food or water. They actually started running out of atmosphere. Now, NASA calculated, I did not do this calculation. I've read this in NASA reports. NASA's calculation was roughly 7% per day. So there was an experiment back in the 80s here on Earth because we wanted to put a habitat or habitable zone on the moon and then put one on Mars. And so we created an experiment here on Earth called Biosphere 2. Now, Biosphere 2 had all the same problems that I'm discussing currently because they tried to mimic construction of a habitable zone as close as they could to what they would build on a different planet. And they didn't have to worry about ionizing radiation too much. They really didn't have to worry about their supply chains too much. And they didn't have to worry about building the device because all of that material was here on the planet and all of that could be done here on the planet. But when it came to thermal expansion, they had a problem because they built the thing out of glass and steel. And steel and glass expand and contract at different rates. So as the days heated up, they put in all these triangular panels and they siliconed them down and everything was airtight. And they believed they wouldn't have gotten past the 7% marker NASA had established because they had perfect control over build. So they thought that 7% would be the maximum loss that they would get. And then one day they had 80% loss. And they went and looked back at their build, and the glass triangles had ruptured off of the out of their seals. It got so hot, and the air inside expanded so much, it was popping the glass panes off. So the glass was actually not failing, but the seal was failing, causing the glass to pressurize off, pop off of these domes. So they became very inventive because they had to solve this problem if they were going to go to the moon or Mars. Is going to happen on Earth, it's going to happen there too. And so they created these lungs, basically. They're inflatable lungs that as the air inside the dome expanded, these would absorb that expansion load. These bladders would absorb the expansion load and bring the pressure inside the dome back down to 14.14 psi, and the glass panels stopped popping off. It's beautiful example of human engineering at its finest. Great system, worked wonderfully. They stopped popping the glass off, and they went from 7% loss per day down to like 2 or 3%. Which was actually really good because they weren't failing their seals due to expansion and contraction. So they actually did NASA total solid there on scientific study, and those bladders worked really well. Now, they wouldn't work on a long-term basis on another planet because they'd probably decay because they're made out of rubberized materials, and they have to be shielded against ionizing radiation. I don't know what to tell you. They will crack and fail. Got to have a better system. Don't know. We're working on it. So they fixed their thermal expansion contraction due to atmosphere expanding. So, yay! So that helps NASA figure out the 7% problem per day. So, in 10 days, you lose 70% of your atmosphere. You got to come back down. You don't have a choice. You have to come back down. You can't stay there. There's not enough atmosphere to live. You don't have enough tanks on board to keep resupplying the atmosphere. Sorry. Okay, so NASA sends up these vehicles. Everything's fine. Nobody talks about anything wrong. Everything's good. And a little grain of sand hits one of the shuttle's windows, and it nearly shattered. Put a little pinhole through the thing. And they were to lose atmosphere slightly faster than 7% suddenly. And they had to fix that hole. They got lucky. They had to fix it. And that's in low Earth orbit. That means there's still atmosphere bouncing around, knocking micrometeorites out. Something the size of a grain of sand nearly collapsed that mission. They're able to fix it. And they were able to return to Earth safely. Go figure. So micrometeorites become a problem because mass times velocity equals force. Well, the faster your velocity, even though you have low mass, the faster you're going, the more force you put out. I could be wrong. So NASA realized that this is a very big problem. Because anything they send up is going to be hit by micrometeorites. Forget large meteorites, okay? Forgetting the fact that we have meteorite storms. Okay, forgetting that fact that every winter we have meteorites come in, little shooting stars, and everybody goes, oh, look, the shooting stars are back. Forgetting that for a second, they got hit by something the size of a grain of sand, not anything bigger. So micro and macro, small and large meteorites are a problem. Again, meteorites are in atmosphere, asteroids are outside of atmosphere. So they're still inside of our atmosphere at some level to call meteorites. Okay? They're not outside of our atmosphere still. So they decided that micro as well as macro meteorites were a problem. So they designed a study, and they took a they took a I don't know what to call it. It's basically an orbiting device, and they put different panels of materials on the outside of the orbiting device in flat sections, and it was a satellite. Sorry, couldn't come up with the word satellite. Go figure. So they have the satellite, and they send it up, and it's going to be retrieved. So it has to be able to come back down and safely and have parachutes and stuff. They sent the satellite up, and has every material known to man on the outside, with relative reason, not materials they wouldn't use. Okay, but every material they would use in a shuttle or a rocket or something that would protect the ship from micrometeorites. They send this thing up, and they leave it up there for some ungodly known time, 8 months, a year, something like that. Whatever. It was a period of time. I don't remember. I was young. And they bring it back down. And when they bring it back down, they safely retrieved it. And they're looking at the object. And maybe it was brought down by a shuttle. They might have put it in a cargo bay and brought it back down. It's possible. Whatever. However they retrieved this satellite. They retrieve the satellite. They get it back down. They bring it down to NASA. And NASA examines it. And the findings were startling because not a single one of those panels hadn't been hit by a micrometeorite. Not one hadn't been hit. It was spinning and moving around the planet, in an orbit, and every panel got hit. 2, not one panel survived the hit. Everything was damaged to a point where they knew that if they left something up in space, it'd be hit by micrometeorites and be broken. And this, I believe, was done in the late 80s. And they gave out the results in the early 90s. And some panels fared better than others is all they could say. If I remember correctly, that's how we got to find out the ceramics worked well. That's how we got to find out titanium worked really well. Other materials didn't fare so well. There's a lot of materials we can't use in shuttle deployment or in deployment of materials up in low Earth orbit. They're just too heavy. It costs too much to ship them. So your heavy steels are out. Things that might have survived those hits were out. High carbon steels were out. And so they're relying on things like aluminum and ceramics and plastics and other metals, whatever they could use, whatever system they devise. And all of the panels took significant damage, which makes you wonder. You get past building the thing in space, you get past the ionizing radiation, you get past your supply chain. You fixed thermal expansion. Not sure if you're going to be able to get past that one. And then you got to micrometeorites. We're not talking macro. We're talking micro. And you get knocked out by a micrometeorite? How much money did you just spend on that object? Yikes. In grade school, in 5th grade, we did a really cool experiment. We took an egg, a fresh egg, not cooked, and we'd take the egg and we'd poke a hole in the top of the egg and poke a little hole in the bottom of the egg, and you'd sit there and go, and take pressure and go, and you blow the egg yolk out the other side. And you'd have an empty egg, and it was kind of cool. You could toss it around in one break, and it's neat and super strong for its size. And and it was a hollow egg. There's no yolk inside. Well, micrometeorite hits one side of the tube, boop, 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 tube, punctures this way, punk, keeps going, punctures that way, punk, and all the liquids and air and gas go out the other side. We call that explosive decompression. Oh, excuse me. Scientists call that explosive decompression. What happens with all the material that's inside said object at 14.14 psi now going to 0? It's all going to get sucked out that hole. Well, you better be able to fix that hole pronto quick before everything gets sucked out of it and it creates a bigger hole. You patch that hole and then patch the other hole somehow. Or patch both of them at the same time would be better because gases are going out both sides. So you have loss of atmosphere and explosive decompression. I wouldn't want to be there. So loss of atmospheres, if they could get that around that, that one's an interesting one because we don't have a material known to man that is not considered porous to hydrogen. Hydrogen's the smallest element we know of, and I'm a welder and a fabricator, and we have to store hydrogen, and we cannot, in the most sophisticated tanks that we have, store hydrogen for long periods of time. It eventually escapes. And not a scientist, but as far as I understand it, the container is considered holy to hydrogen because it's molecules. And hydrogen's a tiny little atom with the single electron. And the electron gets out and goes orbiting out here, wing, 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 on the outside of the molecule. And where does the nucleus go? It just slips right past the molecules and goes with the electron. Because they're bound together. I don't make it up. I could be wrong. But we found in the gas industry, supplying hydrogen to welders and to scientists and to other people in the fields that need the hydrogen, that we had to tell them there's a timestamp on this bottle. From the second they fill it, X day, you're going to lose so many PSI. So you have to use the product in a timely fashion because hydrogen escapes. And it's not out of the seals necessarily. The seals could be good. The valves could be good. The seals could be good. But the cylinder itself is considered porous compared to the size of the hydrogen atom. Now, some scientists out there is cringing and crying and going, no, it's not true. It's not true. Well, give me a different explanation of why the hydrogen doesn't stay in the bottle if all the seals are good. I'm waiting. So, if we lose hydrogen, you will eventually lose water, and you cannot survive in a pure oxygen atmosphere. And that's not going to work because that's considered a loss of atmosphere. And if you have a loss of atmosphere, it doesn't matter what you put up there or how. You lose your atmosphere, you're out. So, the proposal was for welding on aluminum in space. Now, that's all great and dandy. Aluminum's a fine material to weld on. And there's plenty of people that do really good welding on aluminum. And there's plenty of machines that weld aluminum perfectly fine. And everything that makes aluminum a great metal for its use makes it terrible for welding. Welding, aluminum has wonderful properties. It's a great transfer of electricity. We replaced a lot of copper in the 40s with aluminum because it was such a great conductor of electricity. And we found out that's a problem because of thermal expansion and contraction, go figure. But as a conductor of electricity, aluminum is very, very excellent. So when you use electricity to weld on aluminum, it wants to transfer those electrons to ground, wherever the ground is. Oh,
Oh, I'm sorry. Are you in space? God, I hope you know where ground is. Okay, sorry, that was a joke. Too many people are crying right now. It's ground is Earth, and you have to dissipate energy somewhere where you electrify the whole system. There's some right now. There's a physicist out there going, no, and he's crying. He's like, no, it doesn't work like that. But we have to have a ground somewhere. You're going to ground everything. Everything's going to become electrified. So aluminum's a great electron mover. It moves electrons very well. 2, it dissipates heat like crazy. It dumps heat so fast that it makes it really hard to weld on because it's dumping its heat and we call it wetting action. It doesn't go into wetting action very easily. It doesn't start mushing around very easily. Even though aluminum's a low temperature melt, not like steel. So it's low temperature melt, but it doesn't go into wetting action. It's very difficult to actually get the puddle to start. 3, aluminum oxidizes nearly instantly in contact with oxygen or air, atmosphere. And that oxygen layer has to be scrubbed off or cracked off. And to do that on Earth, we use AC welding, or we use a scrub brush or some mechanical way to scrape off the oxide layer. You can't do that in space with automated welding. So are you going to use flux cord? Because you got to get through the oxide layer and you have to have some flux to pop the oxide layer off. Are you going to use AC versus DC welding? AC welding is alternating current, so it pops the oxide layer off as it welds it. Are you going to use pure DC current because you're using a battery? And batteries are DC only. I don't know of any AC batteries. Or are you going to convert DC power to AC and have a loss of energy in translation and then send it through your little electron beam welder and then hope and pray? Because I really hope that you figured out how to clean the prior metal, before you start welding it, because that oxide layer will scrub the mission. Just saying. So aluminum is a really difficult metal to weld, and we can TIG it, we can MIG it, we can arc weld it, we can oxyacetylene weld it, oddly enough. You can propane weld it if you have the right equipment. I'm sure you can laser beam weld and electron beam weld it perfectly fine if you have the right equipment. Great, wonderful. If you've figured out how to get the oxide layer off, you will successfully weld in space. Okay, so you've created this device, you've fixed ionizing radiation, you fixed your supply chains, you've figured out thermal expansion and contraction and Hull stress. You've somehow protected the system against micro and macro meteorites. You figured out the loss of atmosphere. You're now welding aluminum. And then you figured out the decay of the orbit, right? Then you got to figure out material fatigue and replacement. So material fatigue is when things expand and contract and they fail. That gets back to expansion and contraction, and eventually every panel there is going to fail at some level. Doesn't matter why, you have to be able to replace the panel and seal the ship or seal the space station or whatever it is that you're making. So if you figured out material fatigue and replacement, good job. You figured out low Earth orbit decay. Then you have to figure out the axis wobble of spinning an object in space. Now, this one's difficult because they don't understand it. And this has to do with torsion forces, as well as your thermal expansion, contraction, and material fatigue. And you're creating G-force stress on those welds by spinning it. Maybe, maybe not. I could be wrong. But as it's spinning, the object's gonna start to wobble on its axis. Even though it's spinning a circle, the circle's gonna start wobbling. How do we know that to be true? I'm not a scientist, but I'm going to tell you what I think. The Earth is rotating at 23.5 degrees, to the best of my knowledge. I could be wrong. It could be 22.5 degrees. I don't care. But the Earth is at its axis, spinning, right? All the way around. The sun is hitting it with radiation, and it's going around the sun. Okay? And as it goes around the sun, it changes its angle just slightly, right? And then changes it back. And that's about 10,000 year cycle. And we call that global precession. I didn't make up the term. You spin a top, pew, and it lands on the ground. It's perfectly spinning super fast, and then gets that wobble, and then falls down. That's the same thing as global precession. But our top is spinning, and it's so huge, and it's been spinning for so long. Its global precession is only a few degrees, right? But it causes massive shifts in our climate. We have 10,000 year climate cycles that we've studied, and we've watched the climate shift over 10,000 years consecutively, roughly the same, enough for us to say that's global precession. Now, on top of that, what people don't recognize a lot of the time is that the moon plays a significant portion in that global precession, because the moon is orbiting the Earth, and the Earth is orbiting the sun, and both the moon and the Earth are orbiting an object. And as it orbits the object, there's gravitational pull from the moon to the Earth, right? And we get tidal effects out of that. And the water bulges towards the moon, and then it flows away when the moon spins around, and the tidal forces flow towards the moon there. And then it sloshes back and forth. And every time the moon circles the Earth, we get these tidal forces, and we get wave action. I don't make it up. I'm not the one that made that up. I'm not the scientist that figured that out. We get bulges from spinning in the center equator of our planet. That's why we're an oblong spheroid. We're more like an egg shape than we are a sphere. So, and then there's all the cutouts for the water, and we're not perfectly round, just so you know. We're bulging a little bit at the center because we're spinning. But then there's tidal effects from the moon. And do you think that effect from the moon's not going to affect the orbital precession of the space station that's spinning? Of course it will. It's going to affect it all kinds. So if you can figure out how to keep that orbit stable without precessing too badly and changing the gravitational pull from the planet, you might be able to keep the thing up there indefinitely. But I'm no scientist, and I'm not going to do those calculations for you. I'm just going to let you know that they have to be done. And that's just the list for today. Oh, I forgot one. Number 7 on my list. You figured all this other stuff out, and you get humans to live on the thing. Well, you have to have supplies and water and materials, and there's ships coming back and forth, and resupply chain happens here and there and there and there. And there's this beautiful effect that happens. The people the people that are living on the space station go, "What's that smell? Man, let's go use some cleaner on it." Oh, you can't, because you can't use anything that would cause the whole station to be aromatically have a problem with the aroma of the atmosphere, because they'll all get sick. So all your cleaners have to be really, really carefully vetted. You'll probably run into hydrogen peroxide a lot, since hydrogen peroxide breaks down into water and oxygen. And you get a technician to pull a panel off, and he turns the panel off, and it's got mold on it. How'd the mold get there? Well, mold spores are so small that they're everywhere. And so the technician cleans off the mold spores, cleans off the zone, puts the panel back, and goes about his business. Smell doesn't go away. How do I know this to be true? The International Space Station and the space station before it had the exact same singular problem. Moisture would get behind the panels and it caused funguses to grow in the dark, warm area that's moist. And the astronauts would complain about the smell, and then they'd open up a panel and there's black mold growing there, or white fungus, or whatever it is that was growing back there. And there's nothing they can do. They can clean the panel, they can put it back, but they can't purge your atmosphere of humidity. They can't get all the moisture out from behind the panels. They basically are stuck with mold or fungus. And anybody that's talked to a doctor that says, hey, what do you do when you get fungus spores in your lungs? The doctor kind of goes, you're kind of screwed. Really hard to treat fungus infections because we found out that we diverged from funguses. So anything that kills the fungus damages us. I don't make this stuff up. Animalia got classified to be divergent from fungus millions and millions and millions of years ago. They created a new kingdom around us, super kingdom, Paistacanta or something like that. You can go check out Paul Stamets' work on that one. And there's some microbiology students that worked it out and figured it out. I'm not that guy. I'm not the scientist. I could have just pronounced that word all kinds of wrong. Don't take Latin or Greek or nothing like that. I failed English as my primary language. Go figure. But if you can't get around the fungal problem, and fungus is everywhere, then you can't go to space. Because the funguses that you carry on your body, you carry to space with you. And all those resupply ships, they can't be sanitized and sterilized perfectly for every shipment, while having the shipments come and go as often as they need to be to resupply the ship or to manufacture the facility or whatever. And just so you know, fungus has the ability to survive in highly radioactive zones in extreme temperatures and stay viable. Again, how do you know, Seth? How do you know any of this? Well, it just so happens that when Chernobyl burned down in 87, or was it 86? It was 86 because I was 10 years old. When Chernobyl burned down in 86, it released cesium all over the landscape and all over the trees and killed a bunch of trees and instantly toxic to everything around it. Well, scientists went in and tried to fix that, and they did, and they didn't fix it, but they covered it with a shield and then covered that with a dome and then brought in a sarcophagus and put that over there. And people were able to come and go more closely to the Chernobyl factory reactor than they've ever been able to since the accident in 86. And in doing so, they take little Geiger counters, which are registering radiation and rads and stuff, and they go beep, 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 and they'd find these little sections of radiation that were extremely high. And they'd look down, and there's a fungus growing there. And what was happening, I don't know the name of the fungus, I could look it up. We have books on this stuff. Okay? So these are books. This is where information comes from, you know. Back here, there's peer-reviewed data in pages and pages and pages. Okay? So books, really good for you. Don't eat them. Use them to think. So they found out that these funguses were uptaking the radioactive cesium 10,000 times the background radiation, forming a mushroom body. And then they're forming a truffle or a fungus that boars would come along and sniff and eat. And then they'd travel 20 miles away and die from cesium poisoning. But what it did is it took a really concentrated amount of cesium. The fungus is broken down, absorbed some of it into their fungal net, put it over here, grab some more, put it over there, concentrate it up into a fruiting body that could be found by a different organism. The organism would chomp it off, take it away, and it would split or diffuse the waste cycle over larger, vaster areas, causing the background radiation to go down. The solution to pollution is dilution. And a fungus was doing it for us. So funguses could live in the International Space Station as long as they have moisture and something to eat. Oh, and by the way, you know, these things, these books, these tell us what funguses eat, right? There's all kinds of data in here on what they eat because they're growing them. These are people growing mushrooms and substrates, okay? Isn't that cool? Okay, well, they found out there's a couple of things. You have warmth, darkness, moisture, and a food source, and a fungus can grow if it has an energy source. The energy source could be radiation. They don't photosynthesize. So they have to make chemical energy, or they have to use radioactive isotopes to grow their fruiting bodies. They have to have an energy source. So typically what do? They break down organic material, and when they run out of organic material, guess what they break down? Inorganic material, like rocks. So could funguses technically eat the ship from the inside out? Mm-hmm. Yep. Yeah, they could. Funguses could actually eat the mineral content of what the ship is made out of. So you have to be very careful about funguses, because guess what? If they can take up a highly radioactive isotope by using oxalic acid to break down the chemicals and the chemical bonds and the chains and the chain reactions and absorb the molecule and send it upstream, they can do it to aluminum. They found it to work really good against diesel oil, VX, which we didn't even know how to break down. They were able to break down sarin gas. They were able to break down things that humans couldn't break down without using high levels of energy. And that's because they believe that the funguses are putting out acids that decay the items and break the molecular bonds, and then they're able to use the molecule to transfer to a plant. So the plant will give it a starch or a sugar, and it will give the plant the nutrient that the plant is requesting chemically. And that's why there's so many plants that require mycorrhizal fungi to survive and to thrive. So if we don't fix the mold issue inside the starship or the space station, regardless of the material that the fungus is eating, because if they can break down VX, which is toxic to everything, and DDT, which is toxic to everything, they can break down oils, then they can break down plastics. If they can break down rocks, they can break down silica out of steels, and they can break down aluminum that your whole ship is made out of. So you got to figure out the fungus problem. And fungus is among us. So that's your list of things to think about today in this video. If you have comments, leave them below. Remember, I'm not a scientist. I could be completely wrong. But when in doubt, read a book. Lots of pages. I don't care if you even just look at the pictures. They're pretty pictures. You like pictures? Pictures. Figure it out. If you can solve the problem, you'll be a billionaire, if not a trillionaire. You can solve a billionaire's problems, they will make you rich. It's fun stuff to think about. Anyways, we need to save this planet here and now. plant more trees, grow more food, solve the problems here on the planet first before you go to space. Have a great day. That, my friends, was just about an hour. Yeah. 3, 2, 1, lift off.